Hey guys, this is Mrs. Harden, and this is Pre-Calculus Chapter 3. Today we are looking at Section 3.3, which is all about piece functions. Our life application for this unit is that you, the student, will see that God's creation displays functions by changing seasons, life cycles, and throughout nature. We use functions to help us explain patterns, and most of these patterns that we're trying to explain are patterns that have been created by God that we are trying to understand. The lesson objective for today is that you, the student, will define and evaluate piece functions, graph piece functions, and determine their domains and ranges, and introduce continuity of a function. Piece functions are functions that require two or more function rules to define them. Now, what we've looked at before with like linear functions, you had one equation or function rule. Y equals 3x plus 7. That's one function rule. Quadratic functions had one function rule. Polynomial functions, one equation or one function rule. Exponential power functions have one function rule or one equation. Piece functions, however, have to be defined by more than one function rule or more than one equation. Each rule applies to a restricted interval or piece of the domain. So we might have one rule for what's happening in quadrant 2 and another rule or another piece over here in quadrant 1. And we're going to take a look at what that looks like, both in equations, but then also graphed. So here's an example of a piece function. You can see that for f of x, we've got two different function rules or equations, depending on the domain. If x is less than 1, then we have to use this function rule. Negative 3x plus 2. But if x is greater than or equal to 1, then we have to use this function rule. So think about which function rule would we use for f of 0? Well, hopefully you said 0 is less than 1, so that's the negative 3x plus 2 rule. And f of 3? Well, 3 is greater than or equal to 1, so that's this function rule. So we're using different function rules for piece functions. Evaluating f of 0, we get that f of 0 equals 2. And evaluating f of 3 using the second function rule, we get f of 3 equals 8. All right, now let's try to graph these functions, this piecewise function, and give its domain and range. We're going to graph one part at a time. This first one is just a linear function, so we would graph that y equals mx plus b. And the second one, the second function, you guys should recognize as an exponential function. So we should be able to look at this and go, okay, it's got a negative slope, so it's going to look something like this. And this one, exponential function, and it's exponential growth, so it's going to look something like this. So we're going to put those two pieces together here. We do need to pay attention to where our endpoints are and whether they're going to be open or closed circles. All right, our domain will be all real numbers. Less than 1 or greater than equal to 1, that goes from negative infinity to positive infinity. There's not a number in the domain that's not covered by one of these two pieces. Okay, if we graph our two functions just like this without worrying about the domain, they look like this. So here's our negative 3x plus 2, and here's our 2x, so you can see that all of our x values are covered or will be covered if we continue these functions. However, we've got to restrict our ranges here because we've been given some restrictions on our domain. We've been told that x is less than 1. So we've got to cut off our linear function that was right here, cut that off and change that to an open circle to represent less than 1. And then our exponential growth function that was right here, we've got to cut this part off because we're told that for this particular function, x is greater than or equal to 1. So we've got a closed-in circle, and we can leave the part of our graph that is greater than or equal to 1. It might be helpful to you when you're first doing piecewise functions to start off by graphing the two function rules without any restrictions in pencil, and then go back later with your pencil and add in your restrictions. So our range, looking at this, our range must be greater than negative 1. You can tell by looking at this that it does not go below negative 1. The greatest integer function is a special type of piecewise function, and it's written like this. F of x equals and then square brackets x. Be careful when you're looking at this that you're not seeing absolute value bars. Instead, we've got these square brackets. So the greatest integer function, represented by this function rule, has the set of all real numbers for its domain, and its range is the set of integers. So all real numbers for its domain, and then the range is the set of integers, remember, represented with the z. I like to think of the greatest integer function as the Price is Right function. So if you've ever watched The Price is Right, you know that when they first come down to the contestants' row, in order to get up on the stage, they have to guess the price of an item. And when they guess the price of that item, they can't go over. So the winner is the person who gets closest to the price of the item without going over. Now, they don't use any decimals, so all of their guesses are integers. So whoever gets the closest integer without going over is the winner. That's kind of what the greatest integer function is. So if we think about 4.5, the closest integer to 4.5 without going over, here's 4.5. 5 would be over, so the closest integer is 4. Or let's take the function number negative 3 halves. Okay, the closest integer to negative 3 halves without going over, there's negative 3 halves, would be negative 2. Negative 1 would be over. So again, that's why I kind of like to think of that as the Price is Right function. It's the closest integer without going over. Okay, what about 3.8? Closest function would be, or the closest integer would be 3. So hopefully you get the hang of that. Closest integer to 10 is just 10. Closest integer to negative 1.3 is negative 2, and so forth and so on. We'll go through those really quickly here. So let's find the set of ordered pairs described by f of x equals square bracket of x. So that's our greatest integer function and this domain. So we're going to plug in each of these numbers into our greatest integer function in order to determine the range. Now this one, there's not a whole lot going on, so we might be able to do it mentally. So the closest integer to negative 5 without going over is just negative 5. The closest integer to negative 3 halves without going over. Hopefully you said negative 2. See if you can do these other 4 on your own. Pause the video, come back and check. Okay, the closest integer to negative 3/4 without going over is negative 1. The closest integer to 0 is just 0. The closest integer to 1/4 without going over is 1. And the closest integer to 5 halves without going over is 2. So you can see we're going to plug in all of these numbers and we're going to get our ordered pairs. We just did those all mentally, but here's what it looks like, all worked out. So that when we're all finished, we end up with this set of ordered pairs that we can then graph. Now, the greatest integer function has a special look to it, a very unique look. And we'll take a look at what that looks like in just a second. So here is our rule for the greatest integer function. So the greatest integer function says f of x equals greatest integer of x equals negative 2 if our value is less than negative 1 but greater than or equal to negative 2. It's negative 1 if our x value is greater than or equal to negative 1 or less than 0, and so forth and so on. That's what these 3 dots mean. Basically, we're always going to go to the closest integer without going over. And when we graph this function, it looks like this. Okay, let's show you how that works by taking a look at the values that you just came up with in our previous example. So we said when x was negative 5, the greatest integer is negative 5. We've got an open circle there because that value is included. We said when x was negative 3 halves, which is right here, then our greatest integer is negative 2, right there. When x is negative 3/4, which is right about here, our greatest integer is here, which is negative 1. When x is 0, our greatest integer is 0. That's included, so it's there. When our number is 1/4, which is right about here, our greatest integer without going over is still 0. And when x is 5/2, so 2.5, our greatest integer is right here at 2. So those are those points plotted out, and you can see that it represents this kind of stair-step graph. So when you see this graph, you know that it is a greatest integer function, or the Price is Right function. Another special type of piecewise function is the absolute value function. And a good way to help you remember what the absolute value function looks like, absolute value is always a v. So the A can stand for absolute or always, and value can remind you that it's always a v. So anytime you graph the absolute value function, you should have a v shape. It's always a v. And the absolute value function is defined as this. The absolute value of x, if x is greater than 0, x, and if x is less than 0, negative x. All right, let's take a look at what that looks like. Find the function described by the function rule, g of x equals 2x minus 3 for the domain, boom, 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 and boom. 6 values. Please notice that the domain is a specific set of points. It is not continuous. So if we were to graph this function, we would graph only these specific points. We would not graph the whole function because it's not giving us a continuous function. We're going to plug in each of those numbers into our absolute value equation, and using order of operations, we find that g of negative 4 is the absolute value of negative 11, which we know to be 11. And g of negative 2 is the absolute value of negative 7, which we know to be 7. Okay, try these other 3, 4 on your own, and then come back and check your work. You should have ended up with 0, 3, 1, 1, 2, 1, and 4, 5. Those are the points that you would then graph on your Cartesian plane. So our basic absolute function rule is x for x and f of x equals the absolute value of x. That's our basic rule. There is no translation. We don't have any plus or minus any other values here. So then our origin would be 0, 0. The vertex of our function, sorry, not our origin, the vertex would be at 0, 0, which is the origin. Remember, absolute value is always a v. So it looks like this. Now let's graph f of x equals x plus 3 and give it domain and range. Now we have a translation. And hopefully you remember those translation rules. You should know whether this is being translated up or down, vertically, or side to side, horizontally. If you're not sure what the translation is, you can always create a chart, plug and chug, just to check your work. Our domain is still all real numbers, because we know absolute value functions will go far left and far right. And our range is going to be greater than or equal to 3. So if you don't know the translation, then you may need to make a table. But this positive 3 tells us to move the function vertically 3. So we take that same absolute value function and just move the vertex up 3. So we don't have to create a table, although you definitely can to check your work if you're not sure about the translation rules. When translating graphs, here's a reminder of those rules. You can also find these translation rules written out for you on page 122 of your textbook if you want to go back and take notes on those rules or see it in writing somewhere else. But if x is replaced by x minus a, where a is a real number, the graph translates horizontally. So if we have x minus 3, an absolute value bar, for example, if a is greater than 0 and 3 is greater than 0, the graph would move a units right, or 3 units right. If a is less than 0, so if we have x minus negative 3, for example, then that graph would move a units left, in this case, 3 units left. Now, because two negatives do make a positive, it's going to be represented like that. So it's going to seem like you're doing the opposite. To move our graph vertically, we've already looked at that. Look at that number that's being added to the y. So y minus b or y plus b, that's going to move our graph up and down. And if g of x equals negative f of x, then they